I spent years of my life calculating exactly how much energy you can extract from a small amount of mass. And that number, once you actually understand it, tells you almost everything you need to know about why no one from Earth has ever visited another star. I'm not going to tell you a comforting story about engineering someday catching up to our ambitions. I'm going to walk you through why the barrier standing between us and the stars isn't a matter of clever design. It's built into the mathematics of the universe itself in ways that have nothing to do with how advanced our technology becomes. Let me start with distance, because people consistently underestimate it, even people who think they've accounted for how underestimated it usually is. The nearest star system to our own, Alpha Centauri, sits about 4.24 light years away. A light year isn't a unit of time, despite how it sounds. It's a unit of distance. The distance light itself travels in a single year, moving at roughly 186,000 miles every second, the fastest anything in this universe is permitted to travel. 4.24 light years works out to approximately 25 trillion miles. I want you to sit with that number for a moment, because most comparisons people reach for don't actually convey it well. The fastest object humanity has ever launched, a spacecraft called Voyager 1, left Earth in 1977 and has been traveling outward, unpowered, coasting on momentum gained from planetary flybys for decades. It moves at roughly 38,000 miles per hour, which sounds enormously fast, and by the standards of anything we've built, it is. At that speed, Voyager 1 would need over 75,000 years to reach Alpha Centauri, and it isn't even pointed in that direction. This is the fastest thing we have ever sent beyond our own solar system, and it would take longer to reach the nearest star than the entire span of recorded human civilization, multiplied several times over. So the first, most obvious barrier is simply that the distances involved are staggering beyond ordinary intuition. But distance alone isn't what makes interstellar travel physically impossible. In the strict sense I want to use that word. Distance is a problem of time and patience. What I want to walk you through is why the physics itself, not merely our current engineering, places a hard limit on how this problem can ever be solved. Everything begins with special relativity, a theory Einstein published in 1905, years before I was born, but one whose implications I spent a great deal of my own career working directly with, because the physics of nuclear weapons is inseparable from the physics of mass and energy that relativity describes. Special relativity tells us something absolute about the universe. Nothing with mass can travel at the speed of light, and nothing at all of any kind can travel faster than it. This isn't an engineering limitation that better rockets might someday overcome. It's a structural feature of space-time itself, as fundamental to how the universe is built as the fact that effects follow causes. The reason mass and light speed travel are incompatible comes directly from the mathematics of relativistic energy. As an object with mass accelerates and approaches the speed of light, its relativistic mass, or more precisely, the energy required to accelerate it further, increases without bound. The closer you get to light speed, the more energy each additional increment of acceleration demands, following a curve that rises toward infinity as you approach that final limit. To actually reach the speed of light, an object with any mass at all would require an infinite amount of energy, not an enormous amount, not more energy than we currently know how to produce. An infinite amount which no civilization, regardless of how advanced, could ever supply, because infinite energy simply isn't a quantity that exists to be supplied. This is where the specific number I mentioned earlier becomes relevant. The relationship between mass and energy that I understood with painful precision during my years at Los Alamos. Einstein's equation energy equals mass times the speed of light squared tells you the maximum energy obtainable if you could convert matter entirely into energy with perfect efficiency. The speed of light squared is an enormous number, which is why even the small mass defects involved in nuclear fission release energy on the scale that leveled entire cities. But even that staggering conversion rate becomes almost irrelevant once you're trying to approach light speed itself, because the energy required to accelerate a spacecraft asymptotically climbs toward infinity as your velocity approaches that final barrier. You could have a starship converting its own mass into pure energy with 100% efficiency, a process far beyond anything nuclear fission or fusion can achieve, and you would still find the energy requirements becoming unmanageable long before you actually reached light speed itself. Let's set aside for a moment the impossible case of reaching light speed exactly and consider something more modest, traveling at a meaningful fraction of it, say 10 or 20%, fast enough that a journey to a nearby star might at least fit within a human lifetime rather than tens of thousands of years. Even this more modest goal runs directly into a problem of raw energy that I don't think people fully appreciate until they see the actual numbers. Consider a spacecraft with a modest mass, say the size of a large aircraft, something on the order of 100,000 kilograms, an ambitious but not absurd figure for a crude interstellar vessel carrying life support, propulsion systems, and everything else a multi-year or multi-decade journey would require. To accelerate a mass like that to even 10% of light speed, using the standard formula for kinetic energy at relativistic speeds, requires energy on the order of hundreds of exajoules, a number so large that it exceeds the total annual energy consumption of the entire human civilization by a significant margin, and that's the energy required just to reach that speed. You would need a comparable amount of energy again to decelerate at the destination, unless you intend to fly past your target star at a meaningful fraction of light speed without ever actually stopping, which defeats much of the purpose of the journey in the first place. This is where the mathematics of rocket propulsion compounds the problem further in a way that I find genuinely underappreciated, even among people who understand the basic energy requirements. Any rocket, chemical or otherwise, has to carry its own fuel, and that fuel itself has mass, which itself needs to be accelerated along with the rest of the spacecraft. The relationship between how much fuel you need and how much velocity change you're trying to achieve is described by an equation developed originally by Konstantin Tsiolkovsky in the early 20th century. That behaves exponentially rather than linearly. Small increases in your desired final velocity require disproportionately large increases in the fuel mass you need to carry, because you're not just accelerating your payload, you're accelerating all the fuel you haven't burned yet as well. For velocities that are a meaningful fraction of the speed of light, this exponential relationship becomes genuinely punishing, even for extremely efficient propulsion methods. Consider a hypothetical antimatter rocket, and I want to be clear that antimatter propulsion, using matter-antimatter annihilation, represents close to the theoretical maximum efficiency any propulsion system could ever achieve. Since matter-antimatter annihilation converts mass into energy with total efficiency, unlike chemical rockets or even nuclear fission and fusion, which convert only a small fraction of their fuel's mass into usable energy, even with a propulsion system operating at this theoretical maximum, the fuel mass required to accelerate a modest payload to a meaningful fraction of light speed and then decelerate again at the destination works out to many, many times the mass of the payload itself, often by factors that make the entire proposition impractical even before you account for the extraordinary difficulty of actually manufacturing, containing, and safely using large quantities of antimatter, something we have never done at any scale beyond a handful of individual particles at a time in laboratory conditions. I want to walk through one more physical barrier because I think it's the one that surprises people most, precisely because it has nothing to do with propulsion or energy at all. It concerns what happens to a spacecraft physically colliding with the material scattered through interstellar space, even though that space appears to any casual observation to be almost perfectly empty. Interstellar space isn't a true vacuum. It contains a very thin but non-zero distribution of gas and dust, individual hydrogen atoms, molecules, small dust grains scattered at low but non-negligible densities throughout the space between stars. At ordinary velocities, this material is utterly harmless. Spacecraft pass through it constantly without any measurable effect. But the danger of interstellar material scales dramatically with velocity, because the kinetic energy of a collision increases with the square of relative velocity, and at a meaningful fraction of the speed of light. Even a single hydrogen atom striking your spacecraft's hull carries kinetic energy comparable to that of a much larger, much slower moving object. At speeds approaching even 10 or 20% of light speed, calculations suggest that a spacecraft would essentially be under constant bombardment from individual atoms and dust grains, each collision releasing energy comparable to a small explosive impact concentrated on a microscopic area of the hull. Over the duration of a multi-year interstellar journey, cumulative damage from this bombardment becomes a genuinely serious engineering problem, one that would require shielding of a mass and sophistication far beyond anything we currently know how to build. Adding yet more mass to a spacecraft already straining under the energy requirements I described earlier in a vicious cycle where every solution to one problem makes several other problems measurably worse. There is a further complication tied directly to relativity itself, one that I find has a particular kind of poetic cruelty to it, because it involves time dilation, the same relativistic effect that, in principle, offers a strange kind of loophole for a traveler's own experienced time, while making the practical difficulty of the journey worse in almost every other respect. As a spacecraft's velocity approaches the speed of light, time dilation means that the crew aboard experiences less elapsed time than observers who remain behind on Earth. This is often presented in popular discussions of interstellar travel as an advantage, a way for a traveler to reach a distant star within their own lifetime, even if centuries pass on Earth during the same journey. And mathematically, this is entirely correct. A crew traveling at a sufficiently high fraction of light speed could, in principle, experience a journey to a distant star system as lasting only years or even months of their own subjective time, even as Earth-based observers watched the corresponding journey take much longer. But I want to be honest about what this loophole actually offers and what it doesn't. Time dilation doesn't reduce the energy required to reach that velocity in the first place. It doesn't make the propulsion problem or the interstellar collision problem any easier to solve. It offers a way for an individual traveler to personally experience a shortened journey at the cost of returning, if they return at all, to a civilization that has aged by however many years, decades or centuries, corresponded to the trip from an outside observer's perspective. It is, in a sense, a one-way door into your own civilization's future, purchased at an energy cost so extreme that we have not identified any remotely plausible way to pay it, even in principle. Using physics as we currently understand it, I want to address directly the idea that seems to offer an escape from all of this, the possibility of somehow circumventing the light speed limit entirely, rather than simply approaching it. This is where discussions of interstellar travel often turn to concepts like the Alcubierre drive, a mathematical proposal developed by physicist Miguel Alcubierre in 1994, decades after my own death, that technically remains consistent with general relativity while appearing at first glance to allow effective faster-than-light travel. The idea in outline works like this. Rather than accelerating a spacecraft through space to approach the speed of light, which special relativity forbids for objects with mass, the Alcubierre proposal imagines instead warping space itself, contracting space-time in front of the spacecraft, and expanding it behind, effectively creating a bubble of normal, flat space-time around the ship that itself moves through the surrounding universe at an effective speed greater than light, without the spacecraft inside that bubble ever locally exceeding the speed of light relative to its own immediate surroundings. Because general relativity places no fundamental limit on how fast space-time itself can expand or contract, only on how fast objects can move through space-time locally, this proposal technically doesn't violate special relativity's prohibition on faster-than-light travel in the way a simple accelerating rocket would. I find this idea genuinely fascinating as a piece of theoretical physics, and I want to give it the credit it deserves as legitimate, serious work within general relativity's mathematical framework. But I also want to be honest about why it does not currently, and may never, offer a practical escape from the barriers I've described. The mathematics of the Alcubierre metric requires, in essentially every version of the calculation performed since 1994, a form of matter with negative energy density, what physicists call exotic matter, something with genuinely negative mass energy, a substance that behaves in ways fundamentally different from every form of ordinary matter we have ever observed or detected in any experiment, while certain quantum effects, such as the Casimir effect, do produce regions of negative energy density under very specific laboratory conditions. The quantities involved are almost inconceivably small, many orders of magnitude smaller than what would be required to sustain even a modest Alcubierre bubble around a spacecraft of any practical size. Some subsequent theoretical refinements of the original proposal, developed by other physicists working through the 2000s and 2010s, have managed to reduce the exotic matter requirements somewhat, but even the most optimistic of these refinements still require quantities and configurations of negative energy density that remain entirely outside anything physics currently understands how to produce, store, or control. There's also a further theoretical complication that troubles many physicists working on this problem. One connected to causality itself, the basic principle that causes must precede their effects, which is deeply woven into the mathematical structure of relativity. Some analyses of the Alcubierre metric suggest that a drive capable of effective faster-than-light travel could, under certain configurations, be used to construct scenarios that violate causality, allowing effects to precede their causes from the perspective of certain observers, a mathematical possibility that many physicists treat as a strong signal that something in the underlying theory is either incomplete or that nature actively prevents such configurations from ever being physically realized, even if the mathematics doesn't explicitly forbid them within general relativity alone. I think it's worth stepping back from the specific technical details and asking why the universe seems constructed this way at all, why the speed of light functions as such an absolute unbending barrier, rather than simply being a very high but ultimately surmountable speed limit. The honest answer, from everything relativity teaches us is that the speed of light isn't fundamentally a statement about how fast light happens to travel. It's a statement about the geometric structure of space-time itself, about the maximum speed at which cause and effect can propagate through the universe at all. Light travels at this speed because light has no mass, and anything without mass is compelled to travel at exactly this limiting speed, no faster and no slower. Everything with mass, meanwhile, is forever confined below it, with the gap between your velocity and light speed determining how much additional energy every further increment of acceleration costs you, a cost that becomes genuinely infinite only in the strict mathematical limit, but that becomes practically insurmountable long before you ever reach that limit. I spent years of my career thinking carefully about the relationship between mass and energy, first in pure theoretical terms, and then in the most practically consequential terms imaginable. Watching that relationship converted into the most destructive weapon human beings had ever built. I understand in a way I think few people have had reason to understand as directly exactly how much energy is genuinely available when you convert mass as efficiently as physics allows. And I want to tell you plainly that even that maximum conversion rate, applied as efficiently as the laws of physics permit, falls dramatically short of what would be required to send a crewed spacecraft to even the nearest star at a speed that would make the journey survivable within a human lifetime, while also solving the problems of interstellar collision shielding, life support across a multi-year or multi-decade voyage, and the sheer structural difficulty of decelerating at the far end without simply flying past your destination entirely. None of this means the barriers are permanent in some absolute philosophical sense, and I want to be careful not to overstate my own certainty here, because physics has surprised careful, confident people before, myself included at various points in my career. It remains possible that some genuinely new physics, not yet discovered or even conceived of, could someday reveal a pathway around these barriers that current theory simply doesn't accommodate. The history of physics includes real examples of apparently absolute limits eventually being reframed, though I want to be honest that in the specific case of the light speed barrier, the evidence supporting its fundamental nature has, if anything, grown stronger and more precisely confirmed in the decades since my own death. Through particle accelerator experiments that have tested relativity's predictions to extraordinary precision, and through astronomical observations, including the black hole physics I've discussed elsewhere, that continue to validate general relativity's core structure in regimes far more extreme than anything available to test the theory during my own working life. What I find myself returning to, thinking about this problem, is a distinction I came to understand slowly over the course of my own career between problems that are difficult because our engineering hasn't caught up yet, and problems that are difficult because the mathematics of the universe itself forecloses the solution entirely. The atomic bomb was, in its own way, an example of the first kind of problem, extraordinarily difficult, requiring years of theoretical and engineering work, but ultimately achievable because the underlying physics permitted it once enough resources and sufficiently talented people were brought to bear on the problem. Interstellar travel, at least travel that would allow a civilization to visit other star systems on anything resembling a human timescale, appears from everything relativity and the practical physics of propulsion and energy tell us to belong to the second category. It is not a problem waiting for a sufficiently brilliant engineer or a sufficiently well-funded program to solve. It is a problem the structure of space-time itself appears to have built directly into the fabric of the universe, long before any civilization existed to want to cross it. I don't say this to diminish the genuine wonder of what we have accomplished, sending spacecraft beyond our own solar system, mapping the structure of galaxies far beyond our own, understanding in remarkable mathematical detail the physics of stars and black holes we will very likely never visit directly. There's a particular kind of honesty required in physics that I've always found more valuable than false optimism, even when the honest answer is less satisfying than the one people want to hear. The universe did not build the stars for us to visit them. It built a set of physical laws, consistent and elegant, and as far as every test we've ever devised can determine, entirely unbending. And within those laws, visiting another star system in any way that resembles the journeys of popular imagination appears to remain not merely difficult, but physically impossible, for reasons that have nothing to do with the limits of our own ingenuity, and everything to do with the limits the universe itself has quietly, mathematically always maintained.